Hello, everyone. What a wonderful evening we've got prepared for you today. Have you ever wondered how the universe came to exist, or how it will end, whether or not we are alone in the universe, and what is the place of human beings in the great cosmic scheme of things? Well, I wonder about questions like that all the time, but then I'm paid to do so. I'm sure everyone out there from time to time has grappled with these great questions of existence. But for most of human history, they've been confined largely to the realms of philosophy and religion. Over the last few decades, however, science has increasingly made contributions so that these questions which people have asked for centuries and centuries may now be on the verge of being answered. One of the people most responsible for that transformation in our understanding of how the world works is the man we have come to listen to tonight, Stephen Hawking. Dazzling advances in astronomy and improvements in our understanding of the world using theoretical physics have led to these tremendous developments that are so exciting and which we are proud to bring to you this evening. This year, we celebrate the centenary of one of mankind's greatest intellectual achievements, Albert Einstein's general theory of relativity. Amid the chaos of the First World War, indeed, in the closing days of the Gallipoli campaign, Einstein presented his now legendary field equations of gravitation. And in this theory, Einstein described gravitation not as Newton had over 2 centuries before, in terms of a force of attraction operating across empty space, but instead in terms of a warping or distortion in the geometry of space and time. In the beginning, only tiny corrections to Newton's theory could be observed. So Einstein's theory soon came to be accepted, but it was relegated to a backwater of physics because the effects were so small. Its most significant accomplishment was in explaining why the universe is expanding, why all the galaxies are flying apart from all the other galaxies, something that was discovered by Edwin Hubble and others in the 1920s. But the subject of cosmology in general, and the term Big Bang in particular, still lay decades in the future. It was only in the 1960s that gravitational theory finally enjoyed a renaissance. The renewed interest was triggered in part by the discovery of weird objects in space, like quasars and pulsars. These objects had such enormous gravitational fields that they could not be understood without invoking Einstein's general theory of relativity. Now, this theory had, by that stage, become notoriously hard to understand and mathematically very challenging. Only a handful of exact solutions to Einstein's field equations were known. When my wife heard that comment last night, she said, "I don't understand this. You have an equation and it has a solution, and you either know it or you don't. What's the problem?" If only it were that simple. In the 1960s, also, there were developments in mathematical techniques that enabled Einstein's general theory of relativity and this warping in the geometry of space and time to be understood much better. There'd been a lot of confusion about the subject and over the interpretation of what these curved geometries meant. And this was especially successful when applied to what we now call black holes. And it was into this revitalized world of gravitational theory that the young Stephen Hawking stepped. I've known Stephen since 1970, when I was a postdoctoral fellow at the Institute of Theoretical Astronomy in Cambridge. And Stephen was the man in the wheelchair in a neighboring office. In those days, he was not yet a celebrity, but I'd read a couple of his papers, and a colleague remarked soon after I arrived, never ignore anything that Stephen Hawking does, and that turned out to be very sound advice. I have enduring memories of Stephen propelling himself backward down the corridor like this in the days when he didn't have a motorized wheelchair, it was a manual wheelchair. Where was he going? He was heading for the library, and it was in the library we used to take our tea break, which, as you know, is a crucial tradition in British life generally, and academic life in particular, because it was over tea that people learnt about each other's theories and ideas, swapped gossip, and generally had a good time. And it was in these informal tea breaks that I discovered Stephen's mischievous sense of humor and his dogged persistence. At conferences and meetings around the world, there would often be tours and sightseeing trips, visits to bars and restaurants and so forth. Stephen would always insist on coming along. I have many memories. For example, carrying him up a very steep flight of concrete steps next to a particle accelerator in Canada so that he could take a look at this view of this enormous machine, carrying him in the wheelchair. And I hasten to add, it was not just me. It took 4 of us to lift him up off the ground. And there were many instances like that. There was another that I remember of going in Newcastle upon Tyne, of going down to the pub on the quayside on a freezing day, none of us with coats. Stephen cheerfully coming along to have a beer with the rest of us. Well, in spite of the success of Einstein's theory, many physicists felt it was somehow incomplete because it was hard to merge with that other great product of 20th century physics, which is quantum mechanics. It was Stephen's visionary application of quantum mechanics to black holes in the mid-1970s that founded an entire new field of theoretical physics. But I'll leave it to Stephen to explain that himself. Over the intervening years, not only astronomy, but cosmology, and I should say that cosmology is the study of the universe as a whole, its origin, evolution, and ultimate fate, that these subjects advanced in leaps and bounds. Cosmologists agree that the universe began with a Big Bang, but they squabble over what, if anything, happened before it. Was the Big Bang the ultimate origin of all physical things, including space and time, or is our universe just an infinitesimal fragment in a vast and more elaborate assemblage of universes with Big Bangs going off like this, scattered throughout space and time in some eternal overall system? Well, back in the 1970s, many people thought that although physics could be applied to the first split second of the universe after the Big Bang, the origin itself, the first event, was off limits, that you couldn't apply science to that. But Stephen felt otherwise, and in a bold proposal that he's going to tell you about, he demonstrated mathematically how quantum mechanics might bring the very origin of the universe within the scope of scientific inquiry. Well, enough of science. Stephen is, of course, well known to many people around the world as an author, indeed one of the best-selling authors of all time. With his book, A Brief History of Time, he was able to reach parts of the reading public that few other scientists could hope to attract. Those of us who struggled to compete began measuring our book sales in millihawkings. Since then, Stephen has extended his literary reach in partnership with his daughter Lucy to include everyone from the age of 8 to 80. And I really do hope that there are some people out there at the age of 8. If there's an 8-year-old in the audience, say hello. Ah! Well, a special welcome. The recent film Theory of Everything, which we're going to chat about later, helps convey the human side of Stephen's remarkable life. But books and films are no substitute for the real person, and tonight we're thrilled to be able to come as close as the laws of physics permit to bringing Stephen Hawking to you in this world-famous opera house. And here to introduce Stephen is someone who has known him all her life, Lucy Hawking. Lucy is a writer with a remarkable skill for communicating science to everyone, but especially to children. Ladies and gentlemen, please welcome Lucy Hawking.
Thank you, Paul. Well done. Well done. Thank you. Good evening, ladies and gentlemen. In a few short minutes, you're going to see my father, Stephen Hawking, appear as a hologram from his home in Cambridge, England. And it's my pleasure to be here with you in person this evening to introduce you to my virtual father. And you can tell that I am genuinely here with you in this opera house because if I were a hologram, I would have asked them to make me look a little taller. Now, unfortunately, we've just heard that my father's molecules have taken a detour via a distant galaxy. And so, in the short delay before he quantum teleports himself into our company, I thought I'd use this opportunity to tell you a little bit more about him. As I'm sure you can imagine, I'm often asked, what is it like to be Stephen Hawking's daughter? What is that like? Recently, I read an account that an astronaut wrote about traveling in space, and he said, flying in space is a strange combination of the deeply ordinary and prosaic, along with the mind-bogglingly incredible. And that, ladies and gentlemen, if you can imagine, as I stand here wondering if my father is going to appear tonight, or whether we will have just an opera house full of static, is what it's like to be Stephen Hawking's daughter. My father is, of course, at the same time both iconic and immediately recognizable, and yet enigmatic and baffling. It's often said that we're all dealt a hand of cards in life, and that the art of living is to know how to play the cards you hold. And so with that in mind, I thought we would take a sneak look at the cards in Stephen Hawking's hand. So, could we pull out our first card from the pack, please? The adventurer. My father has traveled the world from Antarctica, Easter Island, Russia, China, Japan, Iran, India, many exotic locations. And I think he inherited his adventurous nature from his parents, who were both intrepid travelers. My grandfather, Frank Hawking, was a doctor of tropical medicine who did pioneering work on malaria and bilharzia. And Frank spent much of his life at work in India and Africa. And in fact, he was on the lawn of the British Embassy in what was then called Leopoldville, then known as the Belgian Congo, when he heard of the outbreak of the Second World War. And as soon as he heard the radio report, he set off on a heroic overland journey to East Africa so he could get a berth back to England and enlist for the war effort. My grandmother, Isabel Hawking, was equally daring and intrepid. She was the second child of 7 of a Scottish doctor, and she went to Oxford to study philosophy, politics, and economics in the 1930s, which was very unusual for a woman at that time. And while she was there, she became a communist, and she stayed a communist for the whole of her life. And Granny had lots of adventures. When she was 95, she let slip that she'd once been arrested in New Orleans on suspicion of being a brothel owner. So, no wonder the son of Isabel and Frank saw no boundary to human endeavour. Could we pull again, please, from the pack? The scientist. Of course, my father is a theoretical physicist, and so he looks for ways to use the laws of physics to explain the universe. And much of this evening is devoted to a discussion of his work, his great discoveries, that the universe had a definite beginning, that universes can spontaneously emerge without the need for a creator to flip the on switch, that black holes are not as black as they've been painted. Or, as I like to sum it up, if you find yourself in a dark place, don't despair, because there's always a way out. Could we draw again, please? Bond villain. Recently, my father revealed that his secret ambition is to play a Bond villain. He likes to imagine himself surrounded by Bond girls and advanced technology so he could say the words, "So, Mr. Bond." Unfortunately for him, he is lacking in a few vital attributes. Bond villains, as a rule, want to keep everything for themselves. All the inventions, all the discoveries, all the knowledge. My father, in contrast, has spent his life disseminating scientific information. He set out to share what he knows with the human race in the hope that this will help with the advance of civilization. Also, he doesn't have a cat. Oh, family man. When I was a child in the 1970s, it was clearly very rare for a disabled person to have children. And I base this on the way that people used to stare at us when we went out together. 2 small blonde children and a man in an electric wheelchair. People would openly stop what they were doing and stare and stare and stare as we went past. And we had lots of difficult moments, such as the manager of a restaurant who asked us to leave when we were in the middle of lunch because he said we were putting other diners off their food. Our family life took a lot of persistence and courage on the part of everyone, especially my mother, whose role in my father's life has been captured now in a film called The Theory of Everything. And I hope now that if a disabled person took their children out for a meal or for a walk, they wouldn't receive the kind of treatment we did back then. And I also hope that the story of our family gives courage to anyone whose family life doesn't look quite the way other people think it should. Communicator. My father's not only a distinguished scientist, but he's one who's fought to communicate his ideas to a general public. Believing that scientific literacy is crucial for everyone, he's tried to find the simplest and most engaging way to get his ideas to the widest possible audience. His bestseller book, A Brief History of Time, received a lot of flack for being a book that people bought and didn't read. So, to my joy, a few years ago, I found a league table of the books most often bought and least read. And guess what? Brief History is not on it. This is the only publishing top 10 not to feature Brief History. Oh, Ladykiller, so keen it's jumped out of the pack. Now, as his daughter, I don't really want to talk about this one. So I'll just show you a nice photograph of him with Marilyn, although it could be Anne Hathaway, Jessica Chastain, Cher, Shirley MacLaine, Jane Fonda, or any of the others. Let's move on. Hero. With so many achievements, it's easy to forget that my father suffered for over 50 years from a neurodegenerative illness called ALS, or MND. This condition has taken away his ability to move his muscles, and it's also robbed him of his natural speaking voice. So now, he communicates through a computer. And this computer is controlled by an infrared device on the side of his glasses, which he operates by the twitch of a cheek muscle. Every word he says, every lecture, book, theory, or discussion has to happen this way. You can try it yourself. Just twitch your cheek muscle and see how many words do you think you would produce if you had to communicate like this. And there can be pauses and delays, and they could happen this evening. So I'd like you to be patient and just think about the effort that's gone into the communication you will hear tonight. And I'd just like you to bear in mind that of all the cards we've drawn this evening, I think hero is the most fitting of all. And now, it is time to hear from the man himself. Hopefully, he has arrived. Let me have a look and see. Dad, Are you there? Is there anybody out there? Well, good evening, Cambridge. This is my father, Stephen Hawking, and here we have John Wood, who's his technical assistant. Can you hear us?
Hello, Sydney Opera House.
Hello, John. Hello. Dad, it's lovely to see you, but I just have to say, you are a little late.
I am operating on Hawking time.
Of course you are. Ladies and gentlemen, Stephen Hawking.
Hello, can you hear me? I can hear you too. Thank you for being here this evening. Although I would love to be there in person, the idea of being the first person to appear as a hologram on the stage at the Opera House is too good an offer to refuse. When I do other speeches, I'm not able to do this. I must point out that this is not the first time I have been a hologram. I was supposedly represented by a hologram in an early episode of Star Trek, The Next Generation. In the episode, I was playing poker with Isaac Newton, Albert Einstein, and Commander Data. I won. I was unable to cash in my winnings of 140 Federation credits. I approached Paramount Studios, but they didn't know the exchange rate. My performance was outstanding. I was very convincing as myself. Almost as convincing as Eddie Redmayne. It is thought to be the subject of a Hollywood movie. And it has put me in a reflective mood. So I hope you will forgive me for looking back over my life and how our understanding of the state of the universe has changed. I will also try to look forward beyond the present horizon. I was born on January 8, 1942, exactly 300 years after the death of Galileo. However, I estimate that about 200,000 other babies were also born that day. I don't know whether any of them were later interested in astronomy. I was born in Oxford, even though my parents were living in London. This was because Oxford was a good place to be born during World War II. The Germans had an agreement that they would not bomb Oxford and Cambridge, in return for the British not bombing Heidelberg and Göttingen. It is a pity that this civilized sort of arrangement couldn't have been extended to more cities. We lived in a tall, narrow Victorian house in Highgate, which my parents had bought very cheaply during the war, when everyone thought London was going to be bombed flat. In fact, a V-2 rocket landed a few houses away from ours. I was away with my mother and sister at the time. Unfortunately, my father was not hurt. For years afterwards, there was a large bomb site down the road, in which I used to play. At that time, during and just after the war, Highgate was an area in which a number of scientific and academic people lived. In another country they would have been called intellectuals, but the English have never admitted to having any intellectuals. All these parents sent their children to Byron House School, which was a very progressive school for those times. I remember complaining to my parents that they weren't teaching me anything. They didn't believe in what was then the accepted way of drilling things into you. Instead, you were supposed to learn to read without realizing you were being taught. In the end, I did learn to read, but not until the fairly late age of 8. In 1950, my father's place of work moved to the northern edge of London, so my family moved nearby to the cathedral city of St. Albans. I was sent to the high school for girls, which despite its name took boys up to the age of 10, but later I went to St. Albans School. I was never more than about halfway up the class. It was a very bright class. My classwork was very untidy, and my handwriting was the despair of my teachers. But my classmates gave me the nickname Einstein, so presumably they saw signs of something better. When I was 12, one of my friends bet another friend a bag of sweets that I would never come to anything. I don't know if this bet was ever settled, and if so, which way it was decided. I had 6 or 7 close friends, and we used to have long discussions and arguments about everything, from radio-controlled models to religion. One of the things we talked about was the origin of the universe, and whether it required a God to create it and set it going. I had heard that light from distant galaxies was shifted towards the red end of the spectrum, and this was supposed to indicate that the universe was expanding. But I was sure there must be some other reason for the red shift. Maybe light got tired and more red on its way to us. An essentially unchanging and everlasting universe seemed so much more natural. It was only after the discovery of the cosmic microwave background, about 2 years into my PhD research, that I realized I had been wrong. My father was very keen that I should go to Oxford or Cambridge. He himself had gone to University College, Oxford, so he thought I should apply there. But at that time, University College had no fellow in mathematics, so I had little option but to try for a scholarship in natural science. I surprised myself by being successful. In the end, I have wound up being a professor of mathematics, but I have not had any formal instruction in mathematics since I left St. Albans School at the age of 17. I have had to pick up what mathematics I know as I went along. When I used to supervise maths undergraduates, I would keep 1 week ahead of them in the course. At Oxford, the physics course was arranged in a way that made it particularly easy to avoid work. I did 1 exam before I went up, then had 3 years at Oxford, with just the final exams at the end. I once calculated that I did about 1,000 hours work in the 3 years I was there, an average of an hour a day. I am not proud of this, I am just describing my attitude at the time, shared by most of my fellow students. Because of my lack of work, I had planned to get through the final exam by doing problems in theoretical physics and avoiding questions that required factual knowledge. But I didn't sleep the night before the exam because of nervous tension, and so I didn't do very well. I was on the borderline between a first and second class degree, and I had to be interviewed by the examiners to determine which I should get. In the interview, they asked me about my future plans. I replied that I wanted to do research. If they gave me a first, I would go to Cambridge. If I only got a second, I would stay in Oxford. They gave me a first. I was 20 in October 1962 when I arrived in Cambridge at DAMT, the Department of Applied Mathematics and Theoretical Physics. I had applied to work with Fred Hoyle, the most famous British astronomer of the time. I say astronomer because cosmology then was hardly recognized as a legitimate field. However, Hoyle had enough students already, so to my great disappointment, I was assigned to Dennis Sharma, of whom I had not heard. But it was just as well I hadn't been a student of Hoyle, because I would have been drawn into defending his steady-state theory, a task which would have been harder than getting across the harbor bridge at peak hour. I hadn't done much mathematics in the very easy physics course at Oxford, so Sharma suggested I work on astrophysics. But having been cheated out of working with Hoyle, I wasn't going to do something boring like Faraday rotation. I had come to Cambridge to do cosmology, and cosmology I was determined to do. At that time, cosmology and gravitation were neglected fields that were ripe for development. So I read old textbooks on general relativity and traveled up to hear relativity lectures at King's College London each week. I followed the words and equations, but I didn't really get a good feel for the subject. At that time, it became clear something was not quite right with me. Already in Oxford, I had noticed that I could no longer row a sculling boat properly. The Christmas after arriving in Cambridge, I went home. It was a very cold winter and my mother persuaded me to go skating on the lake in St. Albans, even though I knew I was not up to it. I fell over and had great difficulty getting up again. My mother realized something was wrong and took me to the doctor. I spent weeks in Bart's hospital and had many tests. They never actually told me what was wrong, but I guessed enough to know it was pretty bad, so I didn't want to ask. In fact, the doctor who diagnosed me washed his hands of me, and I never saw him again. He felt that there was nothing that could be done. In effect, my father became my doctor, and it was to him that I turned for advice. At first I became depressed. I seemed to be getting worse pretty rapidly. There didn't seem any point working on my PhD, because I didn't know if I would live long enough to finish it. But then the condition developed more slowly, and I began to make progress in my work. After my expectations had been reduced to zero, every new day became a bonus, and I began to appreciate everything I did have. While there's life, there is hope. And there was also a young woman called Jane, whom I had met at a party. Getting engaged lifted my spirits, and I realized if we were going to get married, I had to get a job and finish my PhD. I began to work hard, and I enjoyed it. The big question in cosmology in the early 60s was, did the universe have a beginning? Many scientists were instinctively opposed to the idea because they felt that a point of creation would be a place where science broke down. One would have to appeal to religion and the hand of God to determine how the universe would start off. Two alternative scenarios were therefore put forward. One was the steady-state theory, in which as the universe always expanded, a new matter was continually created to keep the density constant on average. By the time I began my research, the steady-state theory was already in trouble with observations, but the final nail in the coffin came with the discovery of a faint background of microwave radiation in 1964. The only reasonable interpretation of the background is that it is radiation left over from an early very hot and dense state. As the universe expanded, the radiation would have cooled until it is just the faint remnant we observe today. But there was a second alternative to a beginning in time, which is a bouncing, or even cyclic, universe. Perhaps the universe had a previous contracting phase, and that it had bounced from contraction to expansion at a high but finite density. This was clearly a fundamental question, and it was just what I needed to complete my PhD thesis. Two Soviet scientists, Lifshitz and Khalatnikov, had claimed to have proved that contraction in general relativity without any special symmetry would always lead to a bounce, with the density remaining finite. This result was very convenient for Marxist materialism, because it avoided awkward questions about the creation of the universe. Lifshitz and Khalatnikov were members of the old school in general relativity. That is, they wrote down a massive system of equations and tried to guess a solution. But it wasn't clear that the solution they found was the most general one. A new approach was introduced by Roger Penrose, which didn't require solving the field equations explicitly, just certain general properties, such as that energy is positive and gravity is attractive. Penrose had showed that once a dying star had contracted to a certain radius, there would inevitably be a singularity, a point where space and time came to an end. I realized that similar arguments could be applied to the expansion of the universe. In this case, I could prove there were singularities where spacetime had a beginning. So Lifshitz and Khalatnikov were wrong. General relativity predicted that the universe should have a beginning. Up to 1970, my main research interest was in the Big Bang singularity of cosmology, rather than the singularities or black holes that Penrose had shown would occur in collapsing stars. My work on black holes began with the eureka moment, a few days after the birth of my daughter, Lucy. While getting into bed, I realized that I could apply to black holes the causal structure theory I had developed for singularity theorems. In particular, the area of the horizon, the boundary of the black hole, would always increase. When two black holes collide and merge, the area of the final black hole is greater than the sum of the areas of the original holes. This suggested that the area of a black hole was like what is called the entropy in thermodynamics. It would be a measure of how many states a black hole could have on the inside, for the same appearance on the outside. But the area couldn't actually be the entropy, because as everyone thought they knew, black holes were completely black and couldn't be in equilibrium with thermal radiation. There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes. In fact, we were so successful with the classical general theory of relativity that I was at a bit of a loose end in 1973 after the publication with George Ellis of our book, The Large-Scale Structure of Spacetime. My work with Penrose had shown that general relativity broke down at singularities. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields governed by quantum theory would behave near a black hole. In particular, I wondered, can one have atoms in which the nucleus is a tiny primordial black hole formed in the early universe? To answer this, I studied how quantum fields or particles would scatter off a black hole. I was expecting that part of an incident wave would be absorbed and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole itself. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. It is summed up in this simple formula, which expresses the entropy in terms of the area of the horizon. And the three fundamental constants of nature, c, the speed of light, g, Newton's constant of gravitation, and h bar, Planck's constant. I am proud to have discovered it. Later work uncovered the deep reason for this formula. General relativity can be combined with quantum theory in an elegant manner if one replaces ordinary time by imaginary time. This is called the Euclidean approach because it makes time become a fourth direction of space. The Euclidean space-time is smooth and contains no singularity at which the equations of physics could not be defined. It solved the fundamental problem that the singularity theorems of Penrose and myself had raised, that predictability would break down because of the singularity. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for 30 years, without much progress, which is what often happens in research. But if you get stuck, it's no good getting furious. You just have to keep thinking about the problem while working on something else. Eventually, I found what I think is its resolution. Information is not lost in black holes, but it is not returned in a useful way. It is like burning an encyclopedia. Information is not lost, but it is very hard to read. In fact, Kip Thorne and I had a bet with John Preskill on the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given him the ashes. The fact that I used to think that information was destroyed in black holes was my biggest blunder. Well, at least it was my biggest blunder in science. During the 1970s, I had been working mainly on black holes, but my interest in cosmology was renewed by the suggestions that the early universe had gone through a period of inflationary expansion, in which its size grew at an ever-increasing rate, like the way prices go up in the shops. In early 1982, I wrote a preprint proposing that the seeds for structures in our universe could be created by quantum effects during inflation. This was basically the same mechanism as radiation from a black hole horizon, except that this time it came from the cosmological horizon. I had used Euclidean methods earlier with Gary Gibbons to work out the temperature of De Sitter space. We held a Nuffield workshop in Cambridge that summer, attended by all the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. Several people contributed to the final answer. This was 10 years before fluctuations in the microwave sky were discovered by the Kobe satellite in 1993, so theory was way ahead of experiment. Cosmology became a precision science another 10 years later, in 2003, with the first results from the WMAP satellite. WMAP produced a wonderful map of the temperature of the cosmic microwave sky, a snapshot of the universe at about 1/100th of its present age. The irregularities you see are predicted by inflation, and they mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density slows the expansion of that region, and can eventually cause it to collapse, to form galaxies and stars. So look carefully at the map of the microwave sky. It is a blueprint for all the structure in the universe. Superseding WMAP, today there is a Planck satellite, with a much higher resolution map of the universe you see here on stage. Planck will test our theories in earnest, and may even detect the imprint of gravitational waves predicted by inflation. This would be quantum gravity written across the sky. The original scenario for inflation was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state, but I thought this was unsatisfactory. Unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. What was needed was a space-time without singularity, like in the Euclidean version of a black hole. After the 1982 workshop in Cambridge, I spent time at the Institute of Theoretical Physics in Santa Barbara. I talked to Jim Hartle about how to apply the Euclidean approach to cosmology. According to this approach, the quantum wave function of the whole universe is given by a Feynman sum over a certain class of histories in imaginary time. Because imaginary time behaves like another direction in space, histories in imaginary time can be closed surfaces, like the surface of the Earth, with no beginning or end. Jim and I concluded that this was the only natural choice. We formulated the no-boundary proposal. The boundary condition of the universe is that it has no boundary. We had sidestepped the scientific and philosophical difficulty of time having a beginning by turning it into a direction in space. In this picture, the universe will be spontaneously created out of nothing. It will start out almost completely smooth, except for the tiny departures predicted by inflation, which then give rise to all the structure in the universe we see about us. Around the time of my no-boundary work, I decided to write a popular book. I thought I might make a modest amount to help support my children at school and the rising costs of my care, but the main reason was because I enjoyed it. While I was writing it, I visited CERN, and I became critically ill with pneumonia and lost my voice due to a tracheotomy. But I kept putting a lot of effort into the book, because I think it's important for scientists to explain their work, particularly in cosmology. I never expected A Brief History of Time to do as well as it did. Not everyone may have finished it or understood everything they read, but they at least got the idea that we live in a universe governed by rational laws that we can discover and understand. There are many ambitious experiments planned for the future. We will map the positions of billions of galaxies, and with the help of supercomputers like Cosmos, we will better understand our place in the universe. Perhaps one day, we will be able to use gravitational waves to look right back into the heart of the Big Bang. Most recent advances in cosmology have been achieved from space, where there are uninterrupted views of our vast and beautiful universe. But we must also continue to go into space for the future of humanity. I don't think we will survive another 1,000 years without escaping beyond our fragile planet. I therefore want to encourage public interest in space, and I've been getting my training in early. So let me finish by reflecting on the state of the universe. It has been a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. Thank you for listening.
Stephen's going to take a short break, but he's coming back a little later to answer some questions from the audience. And we're going to use this opportunity, Lucy and I, to talk about the film, Theory of Everything. So let's sit down. We're going to see some film clips in a moment, but first I've just got my own observation that for me it was really weird to go and see a film where I know most of the characters in the film, the real people. But
I felt very much the same.
how much
Paul.
more weird
Yes.
it would be for you
It was even
when you
stranger.
appear in the film.
Yes, because I was watching the film and you get very drawn into the story of these two nice young people, Jane and Stephen, and I was watching thinking, oh, I like these people, aren't they lovely? And, oh, God, they've got together, isn't that wonderful? And now, oh, they've had a baby. So I go, oh, my goodness, that's me. That was a very, very strange moment. A few years ago, a very wise friend of mine said to me, he said, you had the sort of childhood that Hollywood makes movies about. And I thought, well, that could never happen. And lo and behold.
So when I saw the film, some of the characters seemed fairly believable, and then others didn't seem quite like the real people. Were there some that stood out for you as that's just like so-and-so?
The portrayal of my father by Eddie Redmayne is the
superb.
performance that has received a huge amount of attention and accolades because it is so pinpoint accurate. And I think Eddie Redmayne put so much effort into his performance and so much research and so much feeling into it. And he did such a great job. He's a very talented actor. So that was absolutely perfect. I was played by a very lovely 6-year-old who did some great skipping. So it's good,
Right.
good skipping.
Right.
By me.
You never seem to grow up much.
I know, I did. The only thing, the timeline in the film is slightly mysterious because it is, after all, a piece of storytelling. So I do seem to be 6 for rather a long time.
Right. I have to say I loved the Dennis Sciamma character because I knew
He was
Dennis very
excellent,
well, and he was
yes.
just like that. But Roger Penrose is nothing like the real Roger.
Quite a few scientists have complained to me about the PhD Viva scene because it's very quick in the film. It's just a few questions. And someone put to me the other day, they said that their PhD Viva was 4.5 hours long. And I did have to say, I don't think anyone's going to make a film about your PhD Viva, sorry.
Well, let's take a look
Let's take a
at
look.
one of the clips from the film, if we may.
So that's tightened up. As you can see, it's height adjustable, and we can change the angle to whatever Steve wants it at. You know, it's cutting edge.
So how does it work?
It uses a very simple interface that scans through the alphabet and selects each letter one at a time. I mean, using this technique, the professor can expect to write about 4 words per minute.
Good. Better than 1 a minute.
Yes, and what I've done is taken the components from a telephone answering system, actually, to convert the written text into synthesized speech. I mean, the voice sounds a little bit robotic, but should we give it a try?
Great.
There's the clicker.
Right hand.
There you go. Welcome to the future.
My name is Stephen Hawking.
It's American.
Is that a problem?
Oh my goodness. Well, is there another voice?
That's the only one they have at the moment.
I think it's great.
I like that scene. I like that scene very much. It's very much as I remember the introduction of the computerized speech machine
And the American voice.
The American voice,
Which
and
Stephen
everyone-
himself always used to make a point about.
He did, yes. He used to say, I'm sorry about my American accent. And of course, when he was in America, people would be like, why? It did lead to a lot of people thinking that he was American.
That's right.
So for a
Exactly.
long time,
Yes.
people believed that, in fact, he was American. But that was genuinely the voice that was available at that time. And of course, technology has moved on. And they can create all sorts of voices now. They can put a lot of texture and variation and accents, and they can age a voice.
Be an Australian female.
He could be pretty much anything he wanted, but that voice is so closely associated
it is.
with himself now and his personality, and I think people associate that sound with him, and so he doesn't want to change it now.
But we both remember the time when he didn't have that device, and
yes.
when his speech became harder and harder to understand. And I can remember these conversations over tea that we were talking about, struggling to follow what he was saying, but there'd always be a student who would translate Stephen says this, Stephen says that. So there'd be this sort of odd three-way conversation going on. And I think you had to do this as well, even though you'd be quite young at the time.
As children, my brother and I were very good at understanding our father. We could understand exactly what he was saying, even though his voice deteriorated and it had a sort of rusty quality to it. But my brother and I could pick out everything he was saying, even though we didn't actually understand what he was saying. So as children, my father would say something, we'd parrot something about the entropy of black holes or the laws of thermodynamics, and I'd be about 7, and I think, I actually have no idea what I just said. And you'd see the scientist he was talking to, their face would clear or it would crowd, and they'd say something back, and we'd be there in this almost like a simultaneous translator. So maybe I caused some problem. Maybe some of it was lost in translation.
Right. Let's watch another clip.
Let's.
In 1979, you talked about the possibility of a theory of everything being discovered before the end of the century.
I now predict that I was wrong.
Professor Hawking, you have said you do not believe in God. Do you have a philosophy of life that helps you?
Well, that was obviously a very powerful moment in the film. What is the interpretation you put on it, on the symbolism there?
Well, some people said they didn't like that moment in the film, but I found it really mesmerizing and very, very emotional, because I used to have a dream in which I would see my father walk, and I've never actually seen him walk. And then when I saw that scene in the movie for the first time, it was like something out of my subconscious projected onto a movie screen. And it was just overpowering in its emotional impact for me, because it was as though I saw my dream come to life, as though I saw my father and what he would look like in middle age without his condition. And it was very, very moving for me. And it's a sort of reverie. It's going inside the mind of somebody who would like to be free and be able to do a very simple thing, which is stand up, walk down a flight of stairs, and pick up a pen. And so for me, that was extremely emotional. I know it didn't resonate for everybody, but I think I said to the director in the end, thank you for putting that piece in. Even if you only put it in for me, the one viewer, thank you anyway.
Well, Lucy, it's been wonderful to get your insights as a member of the family, as well as someone who's following the signs. You know the words, at least.
I do, yes.
And what we're going to do is get your father's reaction to the film. So, ladies and gentlemen, let's thank Lucy once again. And by miracles of modern technology, bring Stephen back. Stephen, are you there? Hello. Lucy and I have been talking about her response to the movie. What is yours? Tell us your response. How did you feel about it?
I was apprehensive about the film because it was based on a book by my former wife. But I was reassured when I read the script, and even more so when I saw the screening. It was surprisingly honest about our marriage. There were many moments in the film that were quite different from reality. For example, the film has me discover Hawking radiation soon after Lucy was born. In reality, that was when I worked out what happens when black holes merge. But it doesn't matter. I won't tell him how to make movies if they don't tell me how to solve the mysteries of the universe. I thought Eddie Redmayne's portrayal of me was very good. He spent time with people with ALS to be authentic. At times, I almost believed he was me. Those who have seen the movie said it made a big impact. To me, it was close as I'll ever get to traveling back in time. I've been telling everyone that the film should have more physics and fewer feelings. But I am a physicist and not a psychoanalyst, so I think that's probably a fair comment from me. I think all films should have more physics in them, although I realize this is a point of view which may not catch on in Hollywood.
Well, Stephen, quite a few people in the audience have sent in questions, and of course we've had to be very selective as to those we will feature tonight, and I'm going to take them one by one. The first is from Maggot William, and it says, in your book, The Grand Design, you explained how the equations that permit the formation of a habitable Earth are so delicately arranged. Don't you think that the most logical answer to why the universe is as it is that it's been ordered into existence by some intelligent, supernatural being or God? What do you say to that?
No.
Right, thank you.
I find very little logic in that answer. It actually conjures up more unanswerable questions. Such as, what was this God doing before creating the universe? Was he building hell for people who ask such questions?
Well, the next question is from, I hope I'm pronouncing this right, Avidis Gazarian. I should say, incidentally, that as you know, Stephen can see us just as we can see him. So if Avidis is in the audience, please stand up. But the question is, Professor Hawking, you've been quoted as saying that physics would be more interesting if the Higgs boson hadn't been found. I'm not going to go into a description of what the Higgs boson is. You should know if you've been reading your newspapers. Now that the Large Hadron Collider is running at much higher energies, there is a hope among some scientists that it will discover new particles. In your opinion, how much would such a discovery change our current understanding of matter and the universe?
I lost another bet over the Higgs boson. I really need to stop gambling. My daughter thinks I have a problem, but I like to make bets in physics. It focuses attention on important questions. I too hope that the LHC can find new particles. We might be lucky and find supersymmetric partners for the known particles. This would revolutionize our understanding of the universe. There is hope this evidence will be found. But this time I'm not going to put money on it.
Well, we have a final question from Samantha Sue. Samantha, please stand up if you're out there. Here we go. What do you think is the cosmological effect of Zayn leaving one direction and consequently breaking the hearts of millions of teenage girls across the world? And I confess I have no idea what I'm talking about, but Stephen, you follow these things much more closely than I do. So what do you say to Samantha?
Finally, a question about something important. My advice to any heartbroken young girl is to pay close attention to the study of theoretical physics. Because one day, there may well be proof of multiple universes. It would not then be beyond the realms of possibility that somewhere outside of our own universe lies another different universe. And in that universe, Zayn is still in one direction. This girl may even like to know that in another possible universe, she and Zayn are happily married.
Well, thank you, Stephen. Apparently you've just mended many broken hearts, at least those of teenage girls, I assume, but I'm afraid it doesn't mean too much to me. Well, time is an endlessly fascinating subject, but there's never enough of it, and we're approaching the end of this fascinating evening. I think it's only appropriate that the last word should go to Stephen Hawking himself. So, ladies and gentlemen, remember, Stephen can see us just as we can see him. So over to you, Stephen.
Thank you, Paul. And thank you as well to my daughter Lucy for making the journey to Australia on my behalf. And a special thanks to the science and technology that has brought me to you tonight. We have a rather ambivalent attitude to science at present. We have come to expect a steady increase in the standard of living that science and technology have brought. But people distrust science because they don't understand it or feel they can control it. The popularity of science fiction like Star Trek is because this is a form of science with which people feel safe. But an understanding of science fact would lay their fears to rest much better. What can be done to harness this fascination with science and give people the background they need to make informed decisions on subjects like the greenhouse effect, nuclear weapons, or genetic engineering? The basis must be what is taught in schools. But school science is often presented in a dry and uninteresting manner. When I wrote a brief history, I was advised that each equation I included with half the sales. I included one, Einstein's famous equation, E equals mc squared. Perhaps I would have sold twice as many copies without it. Scientists and engineers tend to express their ideas by equations because they need to know the precise value of quantities. But for most people, a qualitative, rather than quantitative, understanding is sufficient. This can be conveyed by words and diagrams without the need for complicated equations. School science can provide the basic framework. But the rate of progress is now so rapid that there are always new developments that have occurred since one was at school or university. Popular science books and articles can help to put across these new developments. But only a small proportion of the population reads even the most successful book. Television is one way to reach a truly mass audience. But television is communication one way only. Now, with the internet, people can answer back and interact. In a way, the internet connects us all together, like the neurons in a giant brain. With such an IQ, what won't we be capable of? I will end on a quote from one of my favorite science thinkers. The late great Mr. Spock. Live long and prosper. Thank you for listening. Now, King Leaf Study.